Thank you everybody at home for better participation, and let's get started. Yesterday we did a I'll say relatively straightforward practice right at the very end with the car being shot up the ramp, right? That's where we left off. Is that right? All right, so today we're going to kind of extend that. And I want to start with, if I was to give a quiz today, this is what it would look like kind of activity. So I'm not giving you a quiz. I'm just saying if I were to give you a quiz, this is what I would expect. All right, so everybody can see this picture okay? I have a little toy cart that's going to go down a track that looks like this. When it makes it to C, it's traveling at 2 meters per second. I have two questions. The first question is, how fast is it going at B? And the second question is, how high did it have to be started to be released from rest and make it to C, traveling at that speed? So two questions. How fast is it traveling at B? And how high would it have to be started in order to be going that fast when it makes it to C? You may assume that this is a frictionless environment. So this would be, if I was to give you a pop quiz today, this is what it would be like. I am very likely to do this tomorrow, first 2 minutes of class for real. Today's just practice. So please take a look at your notes. I hope that they can help you and see if you can't put together what those two answers are. I'll give you 2 or 3 minutes. My oldest daughter has all 3 of her college finals today. Not one professor would budge or move them. So she begins in 20 minutes with the first one. She has 6 hours of exams today. 3 2-hour exams. Man, that sucks. And they're all engineering exams too, so they suck worse. So, but you'll be all done. All right, that's about all the time it should take you to do this question. Believe it or not, it shouldn't be any harder than that. It should be that fast. And you might not believe that that's true, but what I'd like to do is I'd like to tell you how you can go about solving this problem in just a minute or two. It's relatively straightforward once you get the hang of it. You have to figure out one important detail. And once you figure out that one important detail, these problems should be a minute. I mean, quite literally 60 seconds. I know I didn't give you the mass. You don't need it. And that's something that you probably will find out pretty quickly, that with a lot of these, you won't need the mass. the first thing you have to figure out is, can you use conservation of energy?
Attention students, please return to your testing locations that you were in yesterday. If you need to go to your first period class to get a pass or anything, you can do that. You do not need to go to the target booth. Just please return the report to your testing locations at this time and just proceed right there. Thank you.
What? Did that make sense to any of you? Good, good, good. Glad to know. All right. So what I mean by that is, if you can deduce that this is a conservation of energy problem, then the energy at all three places has to be the same. The best way to deduce that, no friction. If they say that there's no friction doing work on the system, then the mechanical energy of the system has to stay the same. So what I would ask you to do to make this go quick is just place a list of the possible types of energy next to each object. For those of you who like to have steps, that's step one. Just draw a quick picture and put those next to each object. I like to describe these as states, that this represents states of the problem. State A, B, and C, bless you. And the object's energy is the same at every state. So what you have to do after you've kind of drafted out the problem and identified the different states is you have to decide on an agreed upon reference level. What's the lowest place the object can go? Now that's easy here. They won't always be easy, which is why I'm kind of being very clear about this step. So make sure you have identified where the lowest place the object can go is. That's obviously here for this problem. But if you're trying to list out a set of steps, put that in there and highlight it. Because if you forget it, that's the easiest way for me to screw you over on the test. Is to put a problem in there where I don't make it easy to figure out where the lowest place is. And that'll be our last example today when we get there. All right, so the next thing you got to do is, once you've kind of drawn your picture, just look at each of these locations. If the object is above your lowest place, then it has gravitational potential energy. So at A, clearly, it's going to have to be lifted up above the lowest place. So it's going to have gravitational potential energy. At B, it's as low as it's going to get. So it has no gravitational potential energy. At C, it's above the lowest place it can be. It does have gravitational potential energy. Next, go back through and determine whether it has the next form of energy. In this case, kinetic. Is the object moving at that location? If it is, it's got kinetic. If it's not, it doesn't. We are releasing it from rest, bless you, at A. So it does not have kinetic energy. If it has energy at some other point in the problem and all that's left is kinetic, then all the energy is probably kinetic. It's probably moving there. So I think it's moving at B. It's got kinetic energy. C, we are told it's moving 2 meters per second, so it definitely has kinetic energy. So you go through, and at each state of the problem, you deduce what kind of energy is there. Once you've done that, you can simply state this is mgh. That's how much energy there is at A. At B, it's going to be 1/2 m, the velocity at B squared. I don't know how fast it is, but I'm just listing out the types of energy that it has at each of these places. And at C, it's going to be mg times 1 plus 1/2 m times 2 squared. So the next thing I've done is I've gone in and put in my known information and listed out the types of energy I deduced the object has at each location. If energy is conserved, these all have to be equal to each other. If we deduce that the energy is conserved, then they all have to be equal to each other. There is bound to be one of these two pairs where I can pair them up and figure out an answer. Meaning I will be given enough information so that when I set two of these states equal to each other, I will be able to deduce an answer. And it looks to me like I could deduce an answer for the velocity right here if I wanted. You don't have to pair them up if they're next to each other. I could pair A and C together if I'd like. You can pair them up in any way you want because the energy at each of these states has to stay the same. So they are all equal to each other. Now, I didn't give you the mass, and there are going to be a lot of times where the mass cancels out. They don't ask how heavy you are when you get on a roller coaster. This is why. So cancel out the masses here. Pretty sure I can figure out how fast it's going to be. And then I can do the same thing if I want to figure out where to start it on the track. Not too terrible, I hope. Now, I don't know about you, but I don't really care about the math part. You guys know how I feel about that. If you're desperate for an answer, though, we'd probably have 10 times 1 plus 1/2 times 4. That's going to have to equal 1/2 times VB squared. I know you guys like to have an answer. So I think the right side's 12. 2 times 12 is 24. So VB is what? Almost 5 meters per second. A little less, square root of 24. Want to see how high I needed to start it? Do the same thing. I'd have mgh equals mg times 1 plus 1/2 m2 squared. Work that out. I'm sure we can figure out how high we had to start it. Cancel all the m's. The right side's still 12 divided by 10. H equals 1.2 meters. Conservation of energy questions should be some of the easiest problems we have to work with. Let's practice another one, okay? I think it appropriate we kind of do a couple of these. So all right, so I have 2 questions. The first one is, how fast is it going when it leaves the track and goes for its jump? And what's the fastest that it goes? So 2 questions. How fast is it going when it jumps? And what's the fastest that it goes? I will choose 2 of you to answer these 2 questions. 1 for each. All right. So hash it out. You want to talk to the person next to you, compare your answers before you get called to, tell me out loud. That'd be great. You guys at home, what I'll do is I will mute you so you guys can talk to each other. There you go. So you guys can talk it out. There's only a couple of you here, so there you go. What does it say on the top? Oh, I'm sorry. On the top of the screen, if you can't see it, it's 1 meter per second. There, I'm sorry. I didn't realize it was above the fold up there. All right, so again, I want to know what speed it hits the ramp and how fast it's going when it's going its fastest. About 60 more seconds, I think.
What did you guys get?
For the fastest velocity, I got the square root of 41, and for the velocity at the end of the ramp, I got square root of 26.
Okay, well, I did something.
You guys about ready?
I'm not sure.
A few more seconds. All right, let's get started. So, Savannah, can you help me out figuring out the fastest? You got 5 point. Can you tell me how you did it? Well, a lot of it makes sense, but I'm gonna step you through it a little bit different, okay? Where do you think is when it's going its fastest? At the bottom. So let's say that this is state B. And where do you think we know the most information about the motion of the object? All right, so we're going to compare what's happening at the very top with what's happening at B. Okay. Do we have gravitational potential energy at the top? How do we know? All right, so we'll say this is the reference level. We're above that. Makes perfectly reasonable sense that we have this. Do we have kinetic energy at the top? How do we know? It's moving. Yep, that's it. So because we know those two things are true, we can say at the top it has both gravitational potential energy and kinetic energy. Excellent. So that's going to be mgh, and it's going to be 1/2 mv squared. So when a cart makes it to here, does it have any gravitational potential energy? Yeah. Why? Perfect. So what kind of energy is it likely to have here? Yeah. So it's sure got kinetic, I'm sure, because that's where all the energy had to go there now. It's like you have two buckets and you poured all the energy into the one bucket marked kinetic. So that's going to be 1/2 m, but we don't know how fast it's going there. So I just have to put v. That's it. So I got an m in every term, so they can all go away. So just like we did last time, we're going to have 20 plus 1/2. And that'll be 20.5 equals 1/2 v squared. Is that what you did? Yeah. So square root of 41, it's not perfect, but you can probably get pretty close. But almost 7, maybe a little less. 6 point what? All right, 6.4 meters per second. Sounds great. That's how fast it's going there at the bottom. Any problem with that, guys? All right, Vanilla, help me out with the speed when it's at the 0.75 meter mark.
I didn't get there yet.
It doesn't really matter, so we're gonna have to go through it.
Okay.
What can you tell me about the kinds of energy it probably has right here?
It has a kinetic energy and a gravitational potential energy.
Okay, so that seems very reasonable. So we'll call this state C, and it has kinetic energy, you just said, 1/2 mv squared. And it has gravitational potential. What can you tell me about the gravitational potential energy that it has?
It's steady.
Well, I meant if I wanted to calculate it, what information do I know about it?
You have a 0.75 meters.
All right, so I can
And
use the fact that it's 0.75 meters above the reference level. So my MGH, where am I going to put that 0.75?
That's okay. M times 10 times 0.75.
Excellent. So what am I going to set this equal to?
1/2 m times v squared.
1/2 m times what squared?
V squared.
Well, I need to find a state where I know what the energy is over here. Is there a state somewhere else in the problem where I know the energy?
At in the middle where the kinetic energy is 0 because it's at its lowest point.
Well, I don't think the kinetic energy is 0 when it's at its lowest point. I think the potential energy is 0 at its lowest
Oh, right.
point. Okay, we can use that spot. That'd be great. How fast is it going there?
0 meters per second.
I don't think so. We just found out that it was going 6.4 meters per second.
But isn't it at the end of the track? Well, no, in the middle, so it's kind of like stopped.
It is definitely not stopped. It rolled down from up here and was getting faster and faster and faster and faster and faster. And when it made it down here, it's going as fast as it's going to go, I think.
Okay, so it's 6.4.
Yeah, that's what Savannah just told us. So yeah, I think Savannah's right. So I think it's 6.4 squared. No, I do think we can cancel out all those M's, but I'll give you a few minutes to try and tell me how fast it's going right here, okay? I'm not letting you off the hook. Cancel all that out. You need to figure out what V is. We'll give you a minute or so. Trying to do the math in my head. How you guys, is this 13 equals 1/2 V squared? Is that right? I don't have a calculator, so, you know. All right, there, I did a little math for you there, Vanilla. You got to do the rest, though. Nick, help her out.
Oh, is my mic unmuted?
What's that?
No, I think my mic was unmuted this entire time. My bad. Hold on, I didn't hear the question.
I got a 2.6.
2.6?
Yeah, for V.
I don't think so. Because I mean, you're gonna get here. If I want to get V by itself, I'm gonna multiply both sides by 2. That's gonna give me V squared equals 26. And I'm pretty sure the square root of 26 is gonna be bigger than 5.
Right.
So what, maybe 5.1? I have my calculator. You have to have your calculator.
Yeah, I got a 5.1. I divided by 2 instead of multiplying it.
I had a feeling. All right, so there we go. Now you guys, you have a taste of what your quiz is gonna be like tomorrow. This is what it is. If you can do this problem, you're gonna be fine. You'll notice I don't give you the math often like this when you don't need it. If you are given it, it's extra information. That doesn't mean that's extra all the time. Notice without M, I would not be able to ask you how much energy there was. To know the amount of energy, you need the mass. So this problem was easy in that it told us how fast it was going, or maybe how high it was, or where it was along the track. But if you are asked for how much energy there is, you will need to know what the mass of the object is. So you can't leave that out. So we used energy, but we never actually found out how much energy there was. Do you guys understand the difference? So bigger objects are going to require more energy in order for them to execute this track, meaning it takes more energy to get that car up to the first part. They're heavier. If you're going to lift it, it's going to take more of your energy to do so. I also want to point out, let's say that I told you that the car had a mass of 2 kilograms. It is not out of the question for me to ask how much work was done lifting the cars to the top of the first track. And you need to be able to understand why that word work is okay there. Even though it looks like a conservation of energy problem, asking how much work was done lifting the cars to the top of the first track is asking you how much potential energy they have at the top of the track. Don't be confused by that. We derived it that way. Be prepared for questions to mix the word work with energy. That was a little bit more of a struggle than I anticipated, but I don't think it's terrible. Do you guys need another example, or can we add a little something to this? Let's do it this way. Let's say 3, this is hard, 2, this is medium, 1, this is easy. Just raise your hand with those. Just let me know how you guys feel. 1.5, okay. All right, see a variety of things. Here, let's try this for a moment. In order to push this forward a little bit, I'm not going to add anything yet, although we are going to have to add elastic potential energy eventually. So based on how much time we have in class, we will touch on that for a minute. I want to show you kind of where these kinds of problems are headed. And I'm going to stick with this roller coaster kind of motif so that, you know, we're being a little consistent. And we had something like that yesterday, right? So let's say that this is Bless you. Has a radius of 0.25 meters. And this is not drawn to scale, so forgive me a little bit. But I need to make sure that there, gotta make this a little bit higher. Let's say that this is unknown. Now, do you remember way back when we talked about the minimum force necessary or the minimum speed necessary to stay inside this loop? You guys remember those questions? Now, this is taking us way back to force problems, but I would like you to tell me what is the minimum speed I have to be able to make it through the loop. This is an old school force question. This is not an energy question. Let's say the car has a mass of 2 kilograms and that the radius of the loop is 0.25 meters. I'd like you to tell me what is the minimum speed in order to stay against the edge of the track at the very top. If you don't remember how to do that, phooey on you, it's in your notes. We did it a dozen times. So do that first. I'll give 2 minutes. I've put almost everything you need to figure it out there on the board. Remember, all of our tests are cumulative. So you're going to have to be able to do this. Jacob, you got the velocity? What do you think it is? 1.58? Trevor, what do you think? 1.58?
Yeah, I got the same.
That's what I think it is too. Just a quick reminder, guys, we will have to do this kind of combination problem. The test is going to be like this. They're going to combine topics together. So we had roller coaster questions where we were asked what the minimum speed was. Now, because we know a little bit more about roller coasters, I can ask you, where do you have to place the car on the track so that it successfully completes the course? What that means is, where do I have to place it so that when it makes it to the top of the loop, it has a speed of 1.58 meters per second? This is a harder question because you have to do the force part of this first. You need to know how fast you're going at the top of that loop. And now that we have that velocity, I know that I will have kinetic energy at the top of that loop because I'm moving. I'm going to have gravitational potential energy at the top of that loop because I am above the reference level. So this is how much energy I have to have in order to successfully make the loop. When I place the car at the top of the track, I'm going to have gravitational potential energy. The question is, where do I have to place the car in order to have enough gravitational potential energy so that I have enough energy to make the loop? It's a tough question. And one I think you guys can do. We now know that's going to be 1/2 times m times 1.58 squared plus mgh is 0.5. You have to realize that you are 2 radii above the ground. So you have to make sure it's a diameter. People make that mistake all the time. It's a little one. I don't want you to make it though. And that has to equal the amount of potential energy we need to start with, mgh. The conservation of energy part of this problem is the same. I'm comparing the energy at one state with the energy at another state. But combining it with force makes this problem a lot more difficult. You'll have to know when to use force and when to use energy. And that's tough. Now, I think you guys can push the buttons and get an answer. I am confident in that. And I'm sure you know it's going to have to be higher than the 0.5 meters from where the top of the loop is. But this is the kind of problem I want you to be able to solve. So we have about 6 more minutes left. I want to talk about something different for a few minutes. But this is the kind of problem I want you to be able to solve. I know you're still working it. So I'll give you a second and then I'll pick on one of you to tell me age. Probably David, because he just can't keep his butt in his chair. All over the place. Such a helpful person. So did you figure it out, David?
The height,
Yeah.
I got 0.62, 0.62 meters.
Anybody else get 0.62 meters? Fits all the things we were talking about. It's higher than the top of this, the point it's at the track, so it has a little bit more potential energy. Seems very reasonable to be 0.62 meters. I'll go with it. I don't know if it's right or not, but it seems okay to me. Now, I'm going to add something to it today. In order to add something to it, we have to talk about something different that we haven't talked about yet. And what I want to talk to you about today is Hooke's law. But really what this is just the law that governs springs. Most all of you have an idea of what a spring is. And although there are a variety of different things that act like springs, we're going to focus our attention on what are known as linear springs. Linear springs are called linear springs because not because they're in a straight line, but because the force you get is proportional to how much you compress them. That's why they're called linear springs, meaning if you pull out the spring a distance x, so I pull the spring outwards, say this distance, the spring pulls back. If you double how far you pull it out, it doubles how much force it pulls back. That's what a linear spring does. It says that the force that's trying to pull the spring back to its original shape is equal to a constant times the displacement. I'm going to say that again because I stumbled a little bit, and I want you to have the words down. A linear spring is one in which the force created to pull it back is proportional to how far you try to extend it. So you pull out on a spring, it tries to pull back to its original shape. That's a linear spring. Yes, ma'am. Sure. A linear spring is one in which the force that the spring applies to pull itself back is proportional to how much you displace it. There's some technicalities here that I have to point out. First, this is the force from the spring. The spring's trying to pull itself back into its shape. Anybody who's ever stretched a rubber band knows exactly what I'm talking about. You let go of the rubber band, it goes back to its shape. That's what this is. It's just like a rubber band. It says that the more I pull it out, the harder it tries to pull itself back into shape. That's it. You already know these things. You've stretched stuff before. And you know that the more you stretch it, the more it tries to pull itself back into shape. That's what a linear spring does. Now, this is technically how you have to write it. This is what the math for that statement looks like. It describes a spring. It has to describe it in both directions because there are some springs where you push in and it tries to push back. And it describes things that you don't think are springs, like a ball. A ball is a spring. If you push in on a ball, the ball tries to push itself back into shape. So all of these things obey what's known as Hooke's law. Anything that tries to put itself back into its shape obeys Hooke's law. Now, there are technical things about Hooke's law that I don't think you need to know, but I'm going to put down here anyways. Displacement's a vector, force is a vector. So I'm supposed to put the vector bars there. And because they're vectors, I've got to put a minus sign here. That minus sign tells me that this force restores the object. If I pull out, the spring pulls back in. If I push in, the ball pushes back out. The negative sign means that the force created by the object tries to restore it back to its original shape. That's what the minus means. K is called the spring constant. It tells you how much force you get. The springs on your car, they have a big spring constant. They have to hold the weight of the car. The slinky, really tiny spring constant. Anybody ever make one of those paperclip jumper things? Has a really small spring constant. Now, that's it for today. Tomorrow we'll cover energy and springs. But I am very likely to ask you to perform a problem first few minutes tomorrow. Very likely. That's not a dare, just letting you know. This stuff's in your homework. You can practice. All right, guys. Thank you for letting me see you today. It was good to see all of you at home. Have a nice afternoon. Hope your classes go well.